Okay, so now after we've introduced what a reaction mechanism is, how it differs from an overall balanced chemical equation, let's take a look at one of the features of a reaction mechanism, which is known as the rate determining step, or sometimes this is abbreviated as RDS, and you'll see this in your textbook and online and other places, and I'll refer to this as RDS from this point onwards. So let's think of a scenario, an analogy, before we actually get into the nuts and bolts of this. So imagine we're thinking of a process, an overall process where we're traveling somewhere, we're going to hop on a plane, and we're thinking about, from the time we get up in the morning and getting to the gate at the airport, right? The gate where you actually board onto the plane. We're not boarding the plane. We're just thinking about waking up and then all the steps involved that will allow us to eventually get to that airport gate. So our starting point is waking up. Our end point is going to be that being at that airport gate. But what are the steps involved? Well, first thing we need to do is need to wake up, obviously, and that's a fairly quick process. We want to pack. We're going for a short trip, so that packing process is going to be fairly fast. Then we need to drive to the airport, and driving to the airport is a fairly fast process as well. We use a car, go on the highway. And then when we get to the airport, we actually have to go through TSA security. And the security line at the airport tends to be, as you probably know, a very slow process. You have to take your shoes off, take your backpack off, your belt, etc., go through the scanner, all that stuff. And that's a slow process. And then once we get through, we can quickly get to the gate. It's not a big airport at OKC. There's only whatever, 10 or 12 gates. We can quickly get there. So if I think about now how quickly I can do that or carry out that overall process, waking up and then getting to the airport gate, how quickly I do that is actually going to depend on whatever that slowest step is, right? So I can do everything super fast, but I'm going to hit a bottleneck once I get to the TSA security checkpoint. So really, the speed at which I can get to the airport gate depends on this slowest step that I have here. Okay, that is going to dictate how fast I can actually get to that airport gate. And that is the same thing that we can apply, same idea we can apply to a reaction mechanism. When a reaction mechanism consists of more than one elementary reactions or elementary steps, the rate law, okay, now, so the overall rate law for the process is actually given by that rate determining step, which is the slowest step, or the slowest elementary step for that overall process. So really, if we have, 3, 4, 5 different elementary steps, to determine the overall rate law, all we need to focus on is that slowest step. That is the rate determining step, right? So it is the slowest step in the sequence, and it dictates the overall reaction mechanism, and is going to dictate the overall rate law for that process. Now, now that we have an idea of what that rate determining step is, the slowest step, slowest elementary step in a reaction mechanism, that mechanism that we propose has to satisfy two very important requirements. The first one is, and we saw this before, when we add together all of the elementary reactions, we need to end up with the overall balanced chemical equation, right? So the stuff on the right side of the elementary steps, we can cancel them out with the same thing we see on the left side of any other elementary steps. And we just sum everything together at the end, and we should end up with the overall balanced equation. This is very similar to Hess's law in terms of how we approach this. And we saw Hess's law back in the thermochemistry section in Gen Chem 1. The second requirement is that the rate determining step, that slowest step, okay, so that's the slowest step, must have the same rate law as that determined from the experimental data, right? And that's going to be critical. That's going to be very important when we start looking at the rate laws for each elementary step, etc. Okay, so let's take a look at a specific example, how we can apply some of these concepts. So the decomposition of hydrogen peroxide, so that's H2O2, that can be facilitated by iodide ions. Iodide ion has a formula I with a -1 charge. So the overall balanced equation for that reaction is 2H2O2 aqueous decomposing to form 2H2O liquid and molecular oxygen, O2 in the gas phase. Now, when we run a bunch of experiments and collect some data and crunch those numbers, we find the experimentally determined rate law to be rate equals K times the concentration of H2O2 times the concentration of I minus. So what this means, right, is that the rate then is first order, the reaction is first order with respect to, so WRT is with respect to H2O2, and then it's also first order with respect to the iodide ion, I minus, and then obviously it's going to be second order overall. Right, remember, this rate law here was experimentally determined for the overall reaction. When you don't see an exponent, remember 1 is understood to be there. That's why we know that it's first order with respect to each of those things. Um, Now we know based on this that the reaction cannot be an elementary reaction. This overall reaction cannot be elementary itself, because if it were, and if this was an elementary reaction, okay, then the rate would simply be equal to K times H2O2 squared, or to the second power, because that's how we treat elementary reactions, right? But it is not elementary because that is not what the rate law that was experimentally determined, that's not what it was found to be. Similarly, what we also see in the experimentally determined rate law is that there is the iodide ion here that shows up, but it is not part of the overall balanced chemical equation. So that introduces a couple things that we need to consider, and we need to reconcile those couple facts. So we can account for that observed rate law, right, the thing highlighted in yellow here, by assuming, so we're going to assume based on that experimentally determined rate law, we're going to assume that the reaction proceeds via multiple steps. And let's say proceeds via 2 elementary steps. Okay, and we're doing that because we know that it's not just a single process, and it's not one step in the reaction mechanism. Because if it were, then that would be um, the rate law, which it isn't, right? So we can say step 1, okay, and we have the H2O2 reacting with iodide to produce H2O plus the iodate, IO minus, and then we'll call this K1 for that rate constant. And then in the second step, right, we have the H2O2 reacting again with the IO minus, and then that proceeds via a rate constant. We'll call it K2 to differentiate them from each other. We end up making H2O. We get O2, and then we get that I minus there at the end as well. So we have these two, we propose these 2 elementary steps. And then we're going to assume here that step 1 is going to be our rate determining step. Okay, that we're assuming this. Okay, rate determining step means it's going to be the slow step in this process. So what we can do from reaction 1, we can write that rate law equation as being K1 times the concentration of H2O2 times the concentration of I minus. All right, and the reason why we would do that is because we want to make sure then that if that is the slow step, the rate law equation for that slow step needs to be the rate law equation for the overall balanced chemical reaction, right? And that's one of the criteria we said previously. So here we can write this for the slow step, and then this is where K subscript 1 is the rate constant from the overall chemical equation, right? So we're making some assumptions, and this is going to take practice when we decide, what we're going to propose, what we're going to assume is slow, etc. Couple things to note. Okay, so when I add these two reactions together, I'm going to write the what we end up with down here. Okay, obviously now I can cancel out a couple things in this process. So first of all, the IO minus appears, it shows up, it's generated at the end of the first step, and then it's used up in the second step. So we can cancel that out, and we can say that the IO minus, right, satisfy the criteria for an intermediate. So it is an intermediate because it's generated in the first step, it's used up in a subsequent step, and it does not appear in the overall balanced chemical equation, right? So it satisfies all that criteria. The I minus, however, is different. So the I minus here, right? So um, it is present at the beginning, and it's also present at the end, right? So we can cancel that out as well when we add these together. I minus is different than an intermediate because the I minus isn't generated. Okay, we add it in at the beginning of the reaction, but then it is also regenerated at the end. So we call I minus, we refer to it as a catalyst. Okay, and all it does is it actually speeds up the reaction. And that's what catalysts do. We'll talk about catalysts in a subsequent section. Okay, so there is a slight difference between them, the intermediate versus a catalyst. A catalyst is something that we use at the beginning, and it reappears at the end, so it's not used up in the reaction. Okay, so it's not used up. Whereas an intermediate is something that is generated, so we don't start with it, right? But it's made, and then it's used up in a subsequent step, so it doesn't appear at the end. So when we add these two reactions together, then we end up with our overall reaction. We have our 2H2O2 reacting to produce, right? So there's nothing else left here on the left side of both of these equations when we cancel it out. To produce on the right side, we have our two H2Os, right? Both of these added together plus our O2. Right, and that's the overall reaction that we saw previously. Okay, so we've seen to it, we've addressed now this whole intermediate thing. We've introduced this catalyst as well, which we'll talk about in a little bit more detail down the road. Now, what we can also look at is how the energy profile for this particular reaction differs or varies from a normal chemical reaction. So if I were to plot the energy profile, okay, so on the x-axis here, we have the progress of the reaction or the reaction coordinate. Okay, and then on the y-axis, that is our potential energy, so PE. So we have our reactants that we're starting with, let's say right about here. And according to our proposed mechanism, this first step is the slow step. So because it's slow, it is probably going to have a very high activation energy. Okay, so our barrier there is going to be super high. Okay, and at the top of it here, we're going to have our transition state, which we represented with that double dagger, or sometimes called the activated complex. And then when we have an intermediate, the intermediate actually forms a little depression or a well in our energy profile diagram. And this is where the intermediate is going to be. It's a short-lived substance. And then we can quickly, once the intermediate is formed, it quickly goes over another energy barrier, and then we end up forming the products here on the right side. Okay, so what we have then, we have a couple things we can note from our energy diagram from this two-step process. We have, first of all, the activation energy for step 1. Okay, that's the difference between the reactants and the top of the barrier. So this is EA for step 1. And then what we have another activation energy that's at the where the intermediate is to the top of the second one, that difference in energy there. That's the EA for step 2. And at the top of this also, we have a second transition state or second activation energy as well. So this first step here is a large activation energy, so it's slow. That's the slow first step. Here we have a smaller activation energy, so it's faster, right? And that's what we'll see when we have these multi-step processes, right? We can identify a couple different activation energies. In this case, we have 2 transition states. We have the intermediate. Remember, the intermediate that we formed there was IO minus in that example. All right, that intermediate, even though it is stable enough that we can maybe observe it, it is going to react quickly to form the products because that second step there is very, very fast compared to the first one. The existence of the intermediate is fleeting, doesn't last very long. Okay, so let's take a look at an example. Here we have the gas phase decomposition of nitrous oxide N2O is believed to occur in a 2-step process. Okay, so we're given here the fact that we have 2 elementary reactions, 2 elementary steps. Step 1, N2O breaks down to form N2, nitrogen, and atomic oxygen. And then in the second step, N2O reacts with that atomic oxygen by a different rate constant to form nitrogen and oxygen. So the experimentally determined rate law, so this is for the overall process, is found to be K times N2O. And based on all of this information, we want to write, first of all, the equation for the overall reaction. Okay, so when we write the equation for the overall reaction, all we're doing is we're adding these 2 together. We're summing them. And when we add them together, whatever we see on the right side of one equation can cancel out with the same thing that we see on the left side of another. So on step 1, that O is generated. You see it on the left side. And then there's nothing else we can cancel out. So the sum there, this is part A, would be equal to, we have 2 N2O2s left over with on the left side. So we have 2 N2O. There's nothing else on the left, so the arrow. And on the right side, we have 2 N2s. And then we're also left with an O2. Right, so that's your overall equation, or the equation for the overall reaction. Right, so because these are 2 elementary steps, what we can also do is we can write the rate law equations for these. Right, and before we do that, let's answer B right now. So B says identify the intermediate or intermediates. So what is an intermediate again? An intermediate is something that is generated in one step and used up in a subsequent step. So the intermediate that we generated here in the first step was O, and then it was used up in the second step. So that satisfies the criteria. So the intermediate there is O, not O2, okay, not molecular oxygen, it's atomic oxygen. That is the intermediate. All right, and then step C, it says identify the rate determining step. So the rate determining step, right, is the slowest step of the reaction, okay? And if you remember the criteria for the rate determining step and the reaction mechanism, etc., we said that the rate law for the overall equation has to be, or is the same for the rate law for the slowest step. Or the rate determining step. So because these are elementary reactions, we can use the stoichiometry in these equations Okay, and we can write out, we don't have to do any experiments. If these are elementary reactions, we can write out the rate law equation. So for step one, we have the rate here is equal to K, we call it K1, because that's our rate constant. And then the reactant that we have is our N2O. Okay, and then the coefficient there is 1, so 1 is going to be our exponent. We can also write the rate law for step 2. So the rate there, so that's rate 1. Rate for step 2 would be equal to the rate constant 2 times. Now we have N2O, coefficient of 1. So N2O raised to the first power. And then we have our O, also coefficient of 1, raised to the first power as well. So all we need to do is, because we're told that the experimentally determined rate law for the overall equation was K times N2O, we just match this up to whatever we came up with here. And obviously, it's the same as this one, where K is equal to K1. So then that means step 1 is our rate determining step. It's the slowest step because the rate law for that step is the rate law for the overall equation. All right, so we want to take all that information, process it, digest it, and then we want to apply it to these different examples.